All right, so I'll get started. So good afternoon, everybody. It's a great
Recording in
pleasure
progress.
to be here today to celebrate with Matteo Bevione for his public defense. I'm Giulia Tagliabue. I'm instructor that I have to introduce myself for the occasion. So I was Matteo's supervisor during the thesis. I guess most of you are familiar with the EPFL system, but there are 3 stages to the PhD process here. First, there is the writing of the thesis, then there is a private defense, which is what Matteo has already passed. And then we come here today to the final public defense. This is more of a celebration step. So Matteo will go and review for us his PhD work, and then he will receive officially his PhD diploma today. So Matteo has started in June 2021. And initially for the first year and a half, sorry, he was an external PhD student, so working affiliated with the LNet, but based in EMPA. And there he was tasked through this European project to develop a system that could harness light from the environment to power a soft robot. And so Matteo started looking in many directions, and then over time, as he will show it to you, he came over this concept of the thermoelectrochemical cells, and he made a great progress in developing a system that is able to harness extremely low temperature heat from the environment to produce electricity that is able to power small devices. And so I guess today we will learn more about the details and maybe also some mentions of future plans and where this can go next. And with that, I will not take more time and leave all the floor to Matteo to tell us about his PhD work.
Thank you very much, Julia, for the kind introduction. And let me start just by thanking you all to be here today and for the time you're dedicating to me. Has been a very nice path so far, so I hope it will continue a little bit longer. But fundamentally today, what has been the journey of my PhD for harnessing waste heat and light with thermoelectrochemical cells. And today we're going to focus about the waste heat part because it's the one I'm in love with. So as basically all the PhD students have started, I started with just a bag full of hopes and not really any direction where to go. So I had to find the path myself at a certain point, but there was always a question that has driven the PhD since the beginning. So the idea was, can we really do something to power up a system just by gathering the energy from the environment? And as you can imagine, this would enable a lot of very cool applications. So we could, in principle, power up a device to monitor structures remotely in not accessible areas. And that would be nice, I would say. The point is that what kind of energy are we going to use? So yes, we need something ubiquitous, and we need something that is there the whole time. So already sunlight is not really the source we want to target. We mostly want to target something that is there the whole time. That's the precise point of having a device work, no? So for this reason, there are some forms of energy omnipresent that generally are called wasted energy. But wasted energy is just a term we use to say we do not know what to do with that. And there are thermal losses, there are kinetic losses, and there are also mechanical losses. But the one more interesting to me, at least, was the thermal losses, because everywhere there is a thermal gradient or something that is hotter than maybe the environment or another surface. So I would say that a waste is only a resource whose value has not been realized yet. So we yet don't know what to do with that. And it's very interesting if we look at the thermal energy to notice that besides being the largest part of the energy wasted, so most of the energy we produce is not really used, it's rather wasted into the form of heat. It's also interesting to notice that there are different levels of heat. So high temperature, medium temperature, or low temperature. And there are already some technologies to deal with the high temperature ones. But for what concerns the low temperature, below 100 degrees, there is not really too much. And if we look inside some reports, at least concern the European area, we notice that there is a lot of potential there. So we have a lot of energy in this range. And the technologies that have been studied and developed so far are what we, most of us at least, already know. There are pyroelectric, triboelectric, and thermoelectric technologies. The pyroelectric relies on the variation of temperature in time, temperature gradient in time. Triboelectric on friction, which is also coupled to heat in some examples. And thermoelectric. Thermoelectric is probably the most known concerning low-grade waste heat. And here, basically, we have a material that is able to develop a current and a voltage going through it when it undergoes a temperature gradient. The point of all these technologies is that they have drawbacks in the low temperature regime. In particular, thermoelectric is not really flexible. It relies on very rare materials, and it's very expensive. So here it comes into play the thermoelectrochemical part, which is fundamentally the twin of the thermoelectric technologies, but just relies on electrolytes and liquid processes and electrochemical processes. So in particular, this has fundamentally the same configuration of a thermoelectric device. We always have a hot side and a cold side, and we have a liquid in between. In the liquid are dispersed some redox couple, which undergo the electrochemical reaction. And in particular, this electrolyte can be either liquid, I mentioned, in water-based, for example, or gel. And the gelled one are particularly interesting for the reason we will see afterwards. But first, let me just introduce to you how this device works. So there are some main effects that we can relate to the production of energy, which is thermogalvanic and thermodiffusion. The thermogalvanic one is precisely what I mentioned before. The redox couple that are in the electrolyte will undergo a redox reaction, whose rate depends on the temperature. So afterwards, there is the thermodiffusion part. Thermodiffusion instead is more the collection of ions at the two sides to develop a further voltage. And then there are some other complementary effects. The complementary effects are the convection, which is predominant in liquid devices, less in gel devices, and electromigration, which is another effect more limited just due to the accumulation of ions at the electrolyte interface. All these effects work synergistically to what is the outcome of these devices. In particular, there are two figures of merits that we need to introduce in order to know how these devices work. And one is the thermopower, which here is indicated as thermopower CBEC. CBEC is the exact equivalent of the thermoelectric devices, but is defined as the variation of entropy, the redox of the redox couple we have in the electrolyte divided by a factor. And the beauty of this is that if we wanted to know what is the open circuit voltage we can actually produce, it's directly just the multiplication of the thermopower and the temperature gradient. So if we fix the cold temperature and we vary the hot side temperature, we will have this nice linear relationship between the voltage and hot side temperature. But where does this entropy difference comes from? So imagine that now you take two iron ions, iron 2, iron 3 plus, and you put that in water. You will have that a certain amount of molecules of the water will surround the ion and organize themselves around the ion. But the point is that one of the two, the 3 plus, will have more strength on the water molecule. And the number of molecules that are ordered around the ion will give what is this entropy difference. So besides the thermopower, there is also this other parameter, which is the normalized power density, which gives you an idea of what is all the power you can produce given a certain amount of temperature gradient. So it's basically defined as the short circuit current multiplied by the open circuit voltage. And if we are representing that as in this graph, the power voltage relationship or current and voltage, we will see that the power voltage has this nice shape. And that's what gives you the 1/4 that's there. You need half of the voltage to have the maximum and half of the current. And if we divide by the temperature square, the temperature gradient square, we will get this MPD, the normalized power density, which is the second figure of merit we need. So just keep that in mind. But fundamentally, what I really wanted to do is not just to investigate the whole theory behind that. I really wanted to develop a device to have an idea of how these things work. And there is a certain configuration that has been studied in the last years, which is an active configuration where we control both the hot side temperature and the cold side. The problem of that is that it's not really a practical application. So if you imagine generally what you have is a hot source, you can put a device on it and that should work. So you not always have the possibility of controlling the cold temperature side. What you want to do instead is to pass then a passive configuration where the cold side temperature is determined by the presence of the environment. So the heat exchange of the cold side with the environment. And this is precisely what I wanted to do. But I faced a first problem, which is if you don't control the cold side temperature, then you will never get a very high temperature gradient, at least not in liquid cells, because the transport of heat throughout the electrolyte will be too fast. So the performance of these devices will be low. The first thing we can think about doing is maybe instead of using a liquid cell, we can use a solid electrolyte, but that wouldn't work because you are preventing the flux of ions, or anyway, you are not any more flexible as we want it to be. So here is where it comes into play my second law of the PhD, which are the hydrogels. And the thermoelectrochemical cells can be quasi-solid, apparently. So I relied on the use of these nice materials. Hydrogels are just basically polymeric sponge. You can develop a hydrogel starting from a monomer, and then these materials will have the nice properties of uptaking a large quantity of liquid, and as you can see in this graph, but fundamentally become the electrolyte themselves. So you will take them, put them in the electrolyte solution, and voila, there you have it. The beauty of that is that we developed also a simulation to understand if this was really possible to then get a large temperature gradient. In this graph, what I'm showing you is precisely what I said, that using just liquids, generally what you get is that you end up pretty soon in a turbulent regime. So if you, irrespective of how thick you make your cell, still you cannot get a very large temperature gradient. So that's very important for us. We then also simulated the hydrogel, and with this material, we could refrain to go into a turbulent regime and really get a very nice temperature gradient. So I was very happy about this result. So I rushed to make my first gel, which was a polyvinyl alcohol based. And fundamentally, we had very nice properties of bending, twisting. I could do fundamentally everything with that, which is good because it's better to have something resistant in the laboratory. And I need to thank these two guys here for helping me realize the first device, which was fundamentally a compression cell where I just placed two identical electrodes across and the hydrogel in the middle, and I could finally start to measure something. So a very important thing that I wanted to understand is that in literature, it's everywhere present the study of how the performance change with the electrode separation. So how thick you make your cells fundamentally. The point of this was that in literature, they say this is absolutely independent. The power you produce is absolutely independent on the thickness of the cell itself, which for me was maybe possible in a liquid, but in a gel, that's pretty odd, especially if we are not in an active configuration. So what they were doing is to fix the temperature of the two sides and then having fundamentally the same results. But for me, the thing was not exactly like that. So thickening the cell would increase both the voltage and the power for this very simple reason that we are increasing also the temperature gradient. So if we make the cell thicker, we will get a larger temperature gradient, we will get a larger power. That's pretty much it. So I also did some practical tests. The graph you saw before fundamentally were simulations. But in practice, it's not really exactly like in theory. So initially, yes, if you thicken the cell, yes, you get a better power output because of the temperature gradient. But if you stretch this too far, then you will get a decrease in the power. And why so? This is particularly evident if we report the maximum power with respect to the electron separation. So here you can see that there is a plateau at first and then a sudden decrease. What I was not taking into account in my first consideration was the fluid flow. The fluid flow, as I said, convection plays a very important role in lipid devices. And convection is basically what drives new redox couple toward the electrode. So if you don't count the convection, you will never have a full picture. What it happens is that even in a hydrogel, we get convective cells that are forming. But if we stretch too far the electrode separation, then we will not have enough thermal power to close the convective cell. And at that point, the velocity of the species close to the electrode, as you can see in this graph here, will just decrease. And if it decreases, you cannot really have new species at the electrode as fast as you want to have. So here it's shown that the voltage fundamentally keeps increasing because your temperature difference keeps increasing, but it's all about the current. It's really all about the current. So you need to find a sweet spot, depending on the condition you have in the surroundings, to produce the largest power output you can. And here comes our first paper. Very happy about that. And at this point, I would think, well, fundamentally, I'm halfway through. I did the first study. I understood pretty much how it works. But there is a main issue with all of these. I really have not so much power. I was producing, I did a good device, but then in the end, compared to the literature, we would not have the same results. So the question is, what are they doing different? There are some ways where we can really improve the performances. And the answer is, of course, yes, there are a lot. We can basically play with the composition of the electrodes. We can play with the composition of the hydrogel. We can play with the nanoparticles, introducing nanoparticles in the system. And we can also change the electrolyte itself, the composition of the electrolyte itself. And this latter is the one that has shown the best results, and also it's the easiest one. So I decided to see what is a good composition of the gel, and in particular of the electrolyte. And here in particular, what I did was changing the supporting electrolyte to a guanidine chloride component. This is fundamentally a chaotropic component that crystallizes one of the two redox species and allows you to get a better diffusion throughout the system. So for this, we could improve, if you look at just at the scale of these two graphs, we simply could improve the power of 10 times, which is pretty nice. And especially comparing these gelled quasi-solid thermoelectrochemical cells, we got fundamentally the very same power performances than liquid devices. The point of this graph here, you see that the scale is much higher, but don't get tricked. The point is that they could fix the temperature of the cold side, so achieve much higher temperature gradient. In a passive configuration, that's pretty much not possible. You rely on the heat transport throughout your device. So yes, we did it. We could get a very good power output. I could see the top, almost there. But what I said at the beginning was, you need to have something that works for a long time. This is just not a one-time energy delivery and that's it. You need something that lasts for a long time. So what really about the long operation? What I did was fundamentally to take this thermoelectrochemical cell and attach to it a resistance and then measure the current. And as you can see, at first we have a very high peak, and then a relaxation in time. And the relaxation depends on the resistance you are applying to it, indicating that fundamentally the higher is the resistance, the slower is the depletion of the species close to the electrode, and then the slower is, the faster is when you get to a stable condition where the diffusion matches the reaction at the electrodes. So, yeah, I won't dwell too much on this as well, but fundamentally, the resistance is a very important point was a very important point to know where is the maximum power output, and you really need to be careful with that, because if it's too high, then your power goes down quite abruptly. So, but besides this, I need to thank these three gentlemen this time. So students were a really important part of my PhD, I would say, that helped me in developing these very nice thermoelectrochemical array. So we could put 9 cells together, and that was done with one purpose in mind. We wanted to see if it's possible to charge an electrolytic battery just using the wasted heat. And I need to thank my colleague here for helping me with the realization of the electrolytic cell. But fundamentally, the setup was very easy. We did the array, we connected the electrolytic cell, and we had a potentiostat in the middle to just measure the current. And the answer to the question is yes, we can. So we could deliver some current to the electrolytic cell and charge it up. The problem with that, we saw initially the current was going down, and this is pretty much expected for the graphs you saw before. But if we wait a little bit of time and then we let it run, we see that the current just keeps decreasing. And there were two main problems there, which was the setup was not really perfectly done because we had just one shot to do it, honestly. But also the second is that we had a failure of one of the components. So if we cannot really ensure that nothing of this is evaporating or leaking in time, then this will never work. So these are all problems that we will face in the future, and I'm already working on that. But the conclusion of this PhD was to prove that also a quasi-solid cell can work in a passive environment, a passive application. And we can really use these devices to have to power up system remotely. So this is pretty much what we did. We could also achieve a very high figure of merits, thermal power, and normalized power density for what it is the instantaneous power delivery. And we also demonstrated the possibility to charge an electrolytic cell in dark condition. Pretty nice. Point is that now we need to fix all the troubles, all the issues we saw. So this leaking, this evaporation must be fixed, and also the configuration has to be done properly. But I will have time to do that in the future because, as you probably know, I won this ignition grant, and I'll have some time to work on it. And now that I started seeing what is going on in the future and how these devices should be done, you realize that at the end of a challenge, there is always another one much, much bigger than the previous one. But this is what makes life worth living, I guess. So I will say thank you very much to all of you, my colleague, my family, my wife, and my kid, for all the support you gave me and for the nice time I had here in EPFL. Thank you, Julia, for hosting me in the laboratory. It was a very, very nice experience. And finally, I would say thank you all for the kind attention.
Thank you, Matteo, for the nice overview. The floor is open for questions. It's your time to pick Matteo's brain or ask him the really troubling question you've been holding up until the very end of his PhD.
Please don't be me.
I've seen you quite many times in the device or chemistry lab making many different gels, playing with their properties, some of them dangerous. In your opinion, what was the coolest and the worst property of your hydrogels?
Well, that's a tricky question because there are so many things to take into account. I didn't really discuss this during the presentation because it would take just too long. But the point is that the composition of the gel is fundamental for what concerns the ionic transport. That's the most challenging part. You really need to tune the porosities, the structure of the gel in order to allow the species to flow well, but in the same time also to prevent the heat transport. So it's a little bit tricky there. The most important properties that I was also looking at is when they are going to I couldn't do much high temperature tests. But when I switched to polyacrylamide and other components, that the issue has been solved. But fundamentally is the composition, the balance between the electrolyte composition and the gel. That was the trickiest part, as you probably know.
Thank you very much for the presentation. I'm not an expert about these applications, but I know a bit of electrochemistry. I was wondering if you anyway thought about the application of catalysts for these electrochemical reactions and what would be the effect?
Well, yes and no. So the problem is that the species that I'm using are pretty aggressive. And there are some catalysts that I could use, one of which was gold at a certain point was studied. The problem is that even gold degrades in time. The other aspect is that I did not have too much time to investigate catalysts, and that was indeed a problem. But now that I spent a little bit of time thinking about that, it's still a matter of finding something that lasts long and is cheap. So the problem of these devices is that you need a lot of area, a lot of them to really have a power output that you can exploit. And if you cannot maintain the cost of this device low, this is not the mentality of academic. I'm thinking about market stuff. So you need to be really cheap. So imagine that a Peltier cell nowadays, if you have to cover 1 meter square, would cost you 6,000 CHF. So you need these to be at least 100 times less expensive. I don't know if catalyst can really help in the trade-off between power and cost. But yeah, it's a nice thing to see for the future.
Thanks.
Thank you very much. I have a small question about your design.
Mm-hmm.
And so if I understood correctly, you have an electrode on one side and another side another electrode.
Yes.
And then you have temperature. Have you thought about having a design electrodes, like electrodes, and then smaller cylinder in the middle?
If you're referring to splice these things on a pipe, then yes, I thought about that. And I wanted to show you something today, but it's better not. because still, this is a project for a startup ongoing, so I'm keeping this a little bit for myself for the moment. But yes, I thought about that. And the answer is that it's trickier than expected to do it, but I already have a first prototype. So we will see together in the next months if it's working.
I have another question.
Please.
So in the beginning of your presentation, you talked about the losses, the heat losses.
Yeah.
In general. And then now with your device, actually, these losses can be enhanced.
Yeah.
You can enhance these devices. So what are the areas that you can use this device?
Well, that's a good question, because initially I was thinking about you just use this device and put them all over the places that have a temperature gradient, so like a house, for example, and then you charge a battery. That was initially my first thought. But as I said, you need a very, very large area to do that. So yes, walls of houses are an idea, but in my opinion, right now, it would be much better to use directly the energy of the device itself, not really to store it. So there are some devices which are basically passive or are very, very low energy consuming, like temperature sensors. And you could directly power up the temperature sensors with these devices, with very small area. And imagine that if you can just control all the temperature devices of this building just with the wasted energy. At least you don't have any usage of the network, the current from the net. And yeah, that's already a good thing. It would be sustainable, at least.
Yeah.
Presentation. You just mentioned you want a stable and cheap device, right?
Yeah.
What if you can replace a chip by also biodegradable?
Tofu, I didn't thought about that, but I thought about either gelatin, which unfortunately it's not working properly because it has a very low melting temperature, but agar or agar that is already used in food industry. That has the sweet spot of melting temperature and the processability. It's a very good material, and I will use that in the future. Sure. But tofu, I didn't consider it. Sorry.
So we're gonna buy a lot of tofu.
Yeah. Well, it's worth the shot.
So it's this food note preamble.
Yeah. I see somebody's
Last
already.
question. Then we get to the more official step. So before I give you your degree, Matteo, I just want to congratulate you again on all the work you've done, because this was really a project you spearheaded from the beginning. Not all the steps were simple, not just in terms of the science, but all that went with it, being a different site, then moving sites. So all of these were also challenging steps. So I think you have to be really proud for all you have achieved, for your resilience, for the results that you have accomplished.
Thank you.
So with this, I'm super happy to award your diploma. So it says officially l'École Polytechnique Fédérale de Lausanne, sous proposition de la Faculté des Sciences et Techniques de l'Ingénieur de CERN, à Monsieur Matteo Bevione, né le 14 janvier 1995, le grade de docteur en sciences. Le candidat a prouvé son aptitude à la recherche scientifique en présentant la thèse intitulée Harnessing Waste Heat and Light with Thermoelectrochemical Cells. Il a réussi l'examen oral exigé par l'ordonnance sur le doctorat dans le cadre du programme doctoral photonique, dont il y a suivi les cours avec succès. Délivré à Lausanne le 9 février 2026. Congratulations. You want to put a picture of your thesis behind the presentation?
Yes.
I think we can pick.
I like more the dragon though, but
You can put the dragon if you want.
yeah. Let's make a serious one first and then.
Okay.
Olé.
You want the one with the dragon?
No. I was just kidding.
Never happened
Ma sì, then let's do it. You know?
Another chance. You won't have another chance.
Allora. Well.
Yes.
It's not finished yet.
Not finished.
Wait, I just.
So this is a good preamble for what comes next.
It is. Oh, so, voila, done. Thank you very much. Can I have a seat?
Oh, yeah.
Ah.
The recording was already stopped.
Yeah.
That's a good idea. So anybody recording online, please stop recording.
Recording stopped.
Okay. Oh, I'll use the microphone. All right. So I guess if there is one thing we all know about Matteo is that science is never just science for him. So we all do science, but Matteo. So for whether he's working in the lab or whether he's at the conference, he likes to talk. And so jokes aside, let's take a moment to appreciate Matteo, because throughout the last 4.5 years of his PhD, he not only mastered the art of research, he have mastered the art of storytelling. Well, so apart from this act of storytelling which he mastered, one of the skills that he really mastered over the years is that he loves cooking. And let's imagine if someone was giving a presentation for us, it would have been that we love eating, j'adore manger. But in this case, Matteo, he doesn't like cooking as much as he likes to cook for others. Yeah. So, and the moment we saw that Matteo mastered these two skills of working and cooking, he took a moment to voluntarily let him suffer in the mountains, because Matteo believes that over the years after suffering the PhD, the bad weather and the high challenging climbs feel quite relaxing. Well, and just as we were thinking that he has taken enough challenges on his plate, he took the chance to take one of the biggest projects in his life, that is becoming a dad. And with all that, he didn't forget to being part of the team we were really lucky to have Matteo in many occasions during this. And at the last, Matteo finally defended. And so congratulations, Matteo. It was a real pleasure of having you as my office mate for the last few years. And congratulations for your PhD defense. Now it's time for you to come.
Oh dear. Run. Doctor. Thank you. Shall I wear this before? Of course. Please wear it. Which side? It's nice. Please wear a lab coat. I'm so afraid to let this fall.
As you never wear it, but this time you should wear it.
Okay, fair enough. Wow. Yeah. Maybe next time I should wear glove first. Thank you very much. Feeling quite. Well, shall I also stop the sharing with? Ciao ciao a tutti. Was fundamentally my family online.
Ciao Teo, bravo. Ciao.
Ciao. Ciao, complimenti.
Complimenti, Teo.
Voilà.